Yeah, I was going to say that we're now going way down the length scale, but I see there's now phones in the title as well, so maybe we're saying it here too. So our next talk will be from Edwin Flikkema, and it will be on global optimization studies of atomic clusters and bombs.
Well, yeah, so welcome to this presentation. Yeah, so I'm Edwin Flikkema. I'm a local here. I'm a lecturer at physics, so sorry to apologize from the start. There will be very little packing or geometry in here, but I thought that this topic, the global optimization of atomic clusters, would be the most relevant to this conference. And I won't have time to talk about the phones, so that was basically also covered by the talk by Wong Chen yesterday. So I'll be focusing on global optimization studies of atomic clusters. So yes, just sort of an overview of the things that I'm interested in research-wise. I've been working on Monte Carlo methods for a while now. I'm interested in global optimization, specifically within the context of chemistry, energy landscape methods, molecular dynamics, and density functional theory. And I've been working on polymers, a little bit on foams, nanoclusters, and glass-forming materials. And it's mainly the nano clusters that I want to talk about. And so I'm interested in various phenomena, topological constraints in ring polymer systems, structure prediction of materials, mixed alkali effect, and amorphization under high pressure. So there are some cartoons here to illustrate those topics there. So what I'm going to focus on is atomic clusters, and I'll be focusing on silica, which is silicon dioxide. And I will be talking about silica as a material. I'll be talking about the modeling of then silica clusters using density functional theory and interatomic potentials. I'll then talk about the global optimization using basin hopping and graph sampling. And then the results will mainly consist of ground state candidates for these silica clusters. So the ones that minimize the interaction energy in a size range of up to 27 SiO2 units. And then I have a separate study using this graph sampling, where I'm specifically looking at so-called fully coordinated clusters there. And if I've got a little bit of time left, I could talk about hydroxylated silica clusters as well. So this one I will skip. That was basically covered by Wong Chen yesterday. Yeah, first to talk about silica as a bulk material. So silica is actually a very diverse material. There's many bulk polymorphs of silica. It's very versatile. So quite often in a bulk, what you have is that each silicon atom is chemically bonded to 4 oxygen atoms, and each oxygen atom is chemically bonded to 2 silicon atoms. So then you can think of a silica material as a network of silicon atoms connected via oxygen bridges. And also this unit of a silicon atom surrounded by 4 oxygen atoms is a pretty rigid tetrahedron. So quite often you can regard a bulk silica material as a network of corner-sharing tetrahedra, where the centers represent the silicon atoms and the corners represent oxygen atoms. And so then we have very many polymorphs of bulk silica, the highest density, lowest energy one being quartz, but you have also much more open structures like this one depicted here. These are generally known as zeolites. Again, there are many of them. And so these zeolites have like pores or cages going through the material, which can be useful, for instance, in chemistry, as for instance, a molecular sieve, where some molecules will be small enough to fit through the pores and other ones will be too large. So then, a bit about the technological importance of silica. There's many applications. I'll just be focusing on the last one, microelectronics. So what we have in a microelectronics chip is the main unit is a field effect transistor, which has a gate. And so there will be a dielectric in between the gate and the silicon surface. And that is usually made out of silica. And as technology is progressing, these devices become smaller and smaller and smaller. So now we're dealing with a silica layer that is of sub-nanometer size. So that's one of the motivations for trying to figure out what silica looks like on the sub-nanometer scale. And obviously, I'll be talking about clusters there, so that's different from the gate dielectric there, but it gives us an idea of what types of structures to expect. So we're going then to focus on these silica clusters. You can sort of think of them as in vacuum there. And so later on, if I've got time, I can talk about what happens if you have water in the environment. So the methodology here is, well, so we need to work out the interaction energy of a silica cluster on the basis of the positions of the atoms. Ideally, we would want to do that at a quantum mechanical level. So those are called ab initio methods. They are accurate, but unfortunately very slow, especially as you go to bigger and bigger clusters. So then empirical force fields, on the other hand, are much faster, orders of magnitude fast to work out the energy, but unfortunately less accurate. So our approach has been to try and get the best of both worlds. So we're using a sort of two-stage process where we use these quick and dirty force fields to produce candidate geometries, and then we put promising candidates into a post-optimization using a more accurate method. In this case, density functional theory, the B3-lib functional and 631 G-star basis set. So that's sort of like an entry-level quantum mechanical method that has a good balance between being reasonably accurate and being reasonably efficient. Now, the force fields that we've then been using is on the basis of a so-called background potential plus electrostatics. And then once we've established this interatomic potential, we're doing global optimization using Basin Hopping, and then something specific that I've been working on, which I was calling graph sampling. So, so a bit about the potential here. So it's a two-body potential. It's dependent on the distance between two atoms labeled with I and J there. So we have an exponential term there, a van der Waals-like term, the minus Cij over Rij to the power 6. That together is the Buckingham part of the potential. And then we have the electrostatic part, which is that Coulomb-like term. So the charges here are actually not the formal charges of the silicon oxygen atoms, but effective charges. And so for these parameters A, B, and C, they come in three different versions: one for silicon-silicon interaction, one for silicon-oxygen, and one for oxygen-oxygen interaction. So there are, in fact, 9 parameters for the ABC part there. So this potential has been used before with 2 different sets of values for the parameters, and they're known as TTAM and BKS. And these were used to model bulk silica. What we've been trying to do then is to come up with yet another set of parameter values, which is trying to reproduce the energetics of silica clusters a bit better. And so that was done on the basis of using DFT data for relatively small clusters as a training set to find the optimal values for the A, B, and C parameters. We didn't change the effective charges there. So once we've established the potential, we want to do global optimization. So the first study uses Basin Hopping. So Basin Hopping is a combination of Metropolis Monte Carlo sampling and local optimizations. So you do a local optimization at every Monte Carlo step. If you have a Metropolis criterion involving energy there to either accept or reject, then we're using the optimized energy here rather than the actual energy. What this then means is that the energy landscape is transformed. So in this cartoon here, if we have the black curve being the original energy landscape, and we do this local optimizations, we get this sort of step profile here where the value of the energy only changes when you go from one basin of attraction of a minimum to another. So I have this sort of step profile there. And that gets rid of barriers between neighboring minima, it makes it easier to do the global optimization, less likely to get stuck. So in more detail here, if you have the sort of standard metropolis Monte Carlo algorithm based on the Boltzmann distribution, what you then do is that if you make a modification of the system compared to the previous step, calculate the new energy, the energy is lower than the previous energy, you always accept, the energy goes up, you pick a random number between 0 and 1 and compare it to this ratio of Boltzmann probabilities here. And if the random number is less, you accept the new configuration. And if it's not, then you go back to the configuration from the previous step. Now, with Basin hopping, wherever there's a reference to an energy there, you use these optimized energies resulting from a local optimization. So, then some technical details there. So I use that potential that I was talking about. The Monte Carlo moves are random displacements of atomic coordinates. We used there was limited memory version of the Broyden, Fletcher, Goldfarb-Shano algorithm for our local optimization. Then the Basin hopping procedure generates loads of these low energy geometries, and we're storing them, and we're sort of keeping the lowest, 200 lowest of them there. And then we search through that and put reasonably looking structures into a post-optimization with density functional theory, which is more time consuming. So that's why you don't use DFT on the fly there. So here are some results after DFT post-optimization. So I was showing the ground state candidate there. So for small clusters with up to 6 SiO2 units, we tend to get these sort of necklaces of so-called 2 rings. We're calling them 2 rings because there's 2 silicons in there. So by the way, so I'm representing these clusters as a network where the yellow vertices represent silicon atoms and the red vertices represent oxygen atoms. So then as we go to 7, 8, and 9, we see a different geometrical motif appearing. And then for 10 and 11, we have something completely different. And then for a while, we sort of see a growth pattern, basically. So like a stack of boxes, sometimes cubic boxes, sometimes more pentagonal prisms with a 2 ring in there. And then that persists. And then going from 22 to 23, there's quite a marked transition there, going from elongated shape to a much more planar shape. And that new geometrical motif sort of persists up until and including 27. There, that's where we stopped. So, because these DFT optimizations are taking a long time. So that was the initial study. And you can see that in all cases, there are a certain number of oxygens that are connected to only a single silicon there. Those are, say, the non-bridging oxygens. In the bulk, these don't appear. So I was now interested in looking into specifically fully coordinated clusters where we don't have these non-bridging oxygens, where every silicon atom is bonded to 4 oxygen atoms and every oxygen atom is bonded to 2 silicons as in the bulk. So there's a number of reasons why we're interested in this. Maybe one of them, the possible use of these clusters for cluster assembled materials, where it might be useful not to have these defects because they would result in a random mess when you try to build the material from that. So there's other more fundamental reasons for being interested in this as well. It's sort of like an example of surface reconstruction, could be a model of that. So in order to specifically sample those fully coordinated clusters, I was trying to do that by doing a Monte Carlo at the level of a graph rather than at coordinate level. The graph meaning the network of silicon-oxygen bonds there. And then you can do then Monte Carlo moves on such a set of graphs. And an example would be to take 2 silicon-oxygen bonds here and rearrange it like this, swapping them around. And then the idea is if you do that starting from a fully coordinated graph, you end up with a fully coordinated graph. So then it's again a very similar Metropolis Monte Carlo procedure here, but now at the level of the graph. So you take the graph from the previous step and modify it a little bit. You're swapping around some of the connections. Then the most challenging thing is to try and represent such a graph as a three-dimensional structure there, three-dimensional geometry. And that's the most time-consuming part of the algorithm, so it might be useful to weed out some unrealistic graphs from the start before you get into trying to find the corresponding geometry. So these, when they fail those constraints, the graph is rejected immediately, and you go back to the graph from the previous step. If it satisfies those constraints, you go to the process of finding the geometry, and then again you get an energy. You do a Metropolis criterion to decide whether to reject or accept the new graph. Now, the most challenging thing is to go from this graph to a three-dimensional realization. And I've been trying to do that using a cascade optimization of 3 different cost functions. So at the first stage, the atoms don't directly interact with each other, can pass freely through each other, but we have bonded interactions there. For each silicon-oxygen pair that should be connected according to the graph, I've basically put a spring between the two to keep them together. There are free-body interactions as well. For an oxygen-silicon-oxygen angle, I have a free-body term that tries to make it as tetrahedral as possible. And for a silicon-oxygen-silicon angle, I've got a free-body interaction that tries to make the angle as close to 180 degrees as possible. So then we do an optimization there, trying to find a rough representation of the graph. And then in the second stage, we start introducing interaction between the atoms, where we get rid of the free body terms there, but we keep the springs in there to hold the bonds together. And then the third stage is just an optimization using that same potential that we used before. So, so then I was talking about a few constraints that we check before trying to find a three-dimensional realization. And one of them is to check whether we still have a connected graph. We could have ended up splitting the graph into separate pieces. We do not allow the introduction of double bonded oxygens there, because then we don't regard it as a fully coordinated geometry anymore. And we do not allow the introduction of triple oxygen bridges, because we know that these are highly strained and high in energy anyway. So then the algorithm produces these nice fully coordinated clusters. That's by design. And so these are the results from the potential rather than from the DFT optimizations. So what we find here for 16 SiO2 units, some of them are based on like a sort of double H ring with 2 rings put in there in various different configurations. So what I have there in the top left is the lowest energy one that we found. And then we go up in energy there to see the different types of geometries that we have there. So then we can do that for 18 as well. We find interesting structures there. Again, going slightly up in energy there. The one here for 24 SiO2 units is quite remarkable. That one is quite low in energy, the lowest energy that we found. It's so low in energy that it sort of popped up in our earlier study using Basin Hopping. It sort of popped up in there as well, though we were not specifically looking for fully coordinated clusters there. It did not quite pop out automatically, but something very similar popped up, but there's some defects, but then we quickly saw that you could heal those defects to make this particular fully coordinated cluster. So then we can go further and further, but it gets progressively more time consuming on a basis of per step, so you cannot do as many steps anymore. So then as we push it to its limits, we're seeing more random structures appear, which I think are just pushing the algorithm to its limits, that we're not sufficiently sampling the energy landscape there to find a true ground state there. A bit about energetics here. So we were very much interested in comparing the energies of these fully coordinated clusters to the ones where you allow them to have these defects. So the red line is for the fully coordinated cluster energy versus number of SiO2 units. The blue line is then when you allow there to be defects. And we see that at 12 SiO2 units, you have a clear energetic gap there where the fully coordinated cluster, lowest one that we found, lowest energy one that we found, is quite a lot of higher energy than the ones with defects. So if you go to 18, that gap has been reduced, and if you go to 24, that gap has become quite small now. So we're sort of conjecturing here that at some point, fully coordinated clusters will be energetically favorable over ones with defects. So I've still got a little bit of time left. Yeah, about 5 minutes. So then I have some time to talk about including water into the picture. So in a more realistic environment, when you're trying to synthesize these particles, there will probably be water around. So then these clusters are likely to react with the water. So that motivated us to introduce H2O into our model. They're not going to remain as molecules. They are going to be pulled apart into separate oxygens and hydrogens there. In order to do the global optimization, now we need to extend the potential to include so now hydrogen into the picture as well. So we used something from the literature by Hassanali and Singer. We simplified the potential a bit. And so then we have here then various combinations of how many SiO2 units, how many H2O units are in there. It might be difficult to see, but the hydrogens are so here connected to these say non-bridging oxygens there. Those are the white vertices at the end there. So then we do that so at various numbers of SiO2 units and various levels of hydroxylation. We can talk about energetics here as well. Look at the change in energy when you do a reaction between a cluster, two clusters form a new one, things like that. So then, so we also have looked at tetrahedrality here, where as you increase the level of hydroxylation, it becomes more tetrahedral. And so, so that's, basically it's to conclude here. I've done various global optimization studies here, followed by then DFT post-optimization to get more accurate so energies and structures there. So the first study using Basin Hopping produced then these benchmark ground state candidates, the size range up to 27 SiO2 units. Maybe the interesting thing is that these geometries are very different from the bulk that we found. And that makes it interesting because then we can expect these clusters to have properties that are different from the bulk, and you could try and exploit that in applications. So then I've been trying to do this Monte Carlo sampling of the space of graphs to specifically sample fully coordinated cluster geometries. Then we have these results here in the size range of about 30 SiO2 units. And then finally, we included water sort of in the picture. I looked at these hydroxylated silica clusters, and these are a bit more realistic, can be used as a starting point for studying things like, or trying to explain, say, the processes going on when you're trying to synthesize zeolites, where these are generally made out of cluster-like precursors to form a zeolite structure. So that's one area where these hydroxylated silica clusters are relevant. And yeah, so that was my talk. And then I'd like to acknowledge a few people: Stefan Romy, Jim Jelfs, David Wells' group in Cambridge. I would like to acknowledge my colleagues here at Aberystwyth University. I would like to thank you for listening.
So you said that you've compared the clusters with the bulk states of the silica. In what ways have you compared them? Have you done like symmetry matching to try to kind of rationalize why certain hypothetical zeolitic structures may not?
Well, so yeah, we've not so directly compared to the bulk, where we used a potential that we used for modeling the bulk as a starting point.
Okay.
And so, yeah, so there are certain structures popping up here, which indeed look like building blocks of zeolites. They're not always the ground state candidate, but they are generally fairly low in energy. So what we're doing is then also not just focusing on the global minimum there, but we're looking at ones slightly higher up in energy.
Have you done any motif matching between the two?
Well, so the structures, they vary a lot with cluster sizes, different geometric motifs at different cluster sizes, and none of them are like quartz. Some of them look like building blocks of zeolites, but there's then other ones that have no sort of like bulk counterparts there. So that's where hopefully these will be useful in having specific properties that are different from the bulk.
It'll be interesting to compare the relative energetics of, say you have something that forms as a precursor to your global optimum. It is very bulk-like in its symmetry. That, I mean, people have been fighting for years trying to figure out why all the hypothetical zeolites don't form.
Yeah.
That could be a rationalization if there's a better cluster optimum compared to a local optimum in the crystal formation.
Yeah, that's right. It is something, we did something along those lines using these hydroxylated clusters to try and explain certain processes in zeolite formation. Yeah, that's a bit of work that I was involved in, and I didn't include here in the presentation. Well, thanks. It's a good suggestions. Yeah.
I was wondering whether such clusters have been synthesized experimentally in the gas phase, and what would be their signature, maybe Raman spectroscopy or something like that?
Yeah, so the closest to doing this experimentally would be cluster beam experiments, where you would be firing a laser, say, at the silica surface, and fragments would be coming off. Now, because it's cluster beam experiments, these tend to be charged clusters, so not exactly what we've been looking at, slight modification there. So that's a way of making these silica clusters. It might not specifically form the global, be very directed towards the global minimum, because then there's also kinetic effects going on there. We had some other ideas about making silica clusters, then starting from hydroxylated silica clusters and sort of burning off the water there. So it's sort of predictive here, this study, where trying to make these in actual real life is a challenge. But when we look at these hydroxylated silica clusters, that's a bit closer to the experiments, because it's a bit easier to make these in a say in an aqueous solution. But obviously then the environment comes into play, so you need to change the vacuum to some kind of model for taking into account an environment there. But it's one of the things that one of the people, Stefan Bromley, has also been working on.
Right. Also, something I haven't fully understood for the Monte Carlo method, the initial configuration. Do you take as an input the calculations from the other algorithm, from the DFT, or do you start from basically just like adding one?
So you can start from different starting points. Theoretically, it shouldn't matter. Theoretically, you're exploring the whole energy landscape, but since you're only doing a finite number of Monte Carlo steps, the choice of the initial structure can matter. So I've been starting from various different initial ones. For instance, this sort of necklace of two rings takes a while, takes quite a few Monte Carlo steps to get from that to a more reasonable structure. So sometimes we would put some sort of cage-like structure as an initial starting point. We can then also, once you've done several of these runs, you can use the best candidate from a previous run as a starting point for the next one, or you can try and be a bit more varied in the hope that you're covering the energy landscape more. So it can be, in order to widen the search, it can be good to start from, say, an unrealistic starting structure, that you're starting high up on the energy landscape, such that you don't necessarily always get into the same funnel, basically, and then ending up with the same ground state candidate each time. So we've varied that. It's even sort of possible to start from sort of random initial coordinates. You need to allow for a bit of Monte Carlo steps for it to actually form a cluster there, but that's sort of doable as well. But then you have to sort of equilibrate, have to do a few initial steps there. And for the coordinated study would start with this like a cage-like initial graph.
Yeah, I forget what N was, but you had a multiplet where the difference in energy levels was less than 0.1% mostly.
Yeah.
I was curious. I mean, I've encountered just for really, really simple things like opposite problems, things where multiple states, but they tend to be fairly far apart. But what I was curious about was whether the rates at which one transitions between those nearby energy levels, whether you've ever tried to look at that might be
almost. It was something I meant to do but never got around to. So you can extend. So first of all, there are many minima with a very similar energy. That's maybe also why silica is a large former. So you can use the global optimization as a first step to an energy landscape analysis.
Can I was curious about how high a little.
Yeah. So then you're going to consider what chemists call transition states as well. So those are basically stationary states with one negative eigenvalue of the Hessian, like a mountain pass connecting to minima there. Once you've got that, then you can look at the energetic barriers between different minima. And there's a clever way of arranging that into a graph, which David Wells calls a disconnectivity graph, which, if you go high up in energy, basically any cluster can transform in another cluster. But as you bring down energy, it starts to separate in different domains there. As you bring down energy, it splits up more, and you can plot that in what David Wells calls a disconnectivity graph. And that gives you an idea about, say, how glass-like, or how it gives you an idea about the dynamics there. So, but it is more difficult to do, especially at the DFT level. Finding transition states is is a lot more complex than just finding minima there. So it's a bit tricky, but it was something that was on my list of things to do. Yeah.
Are you you're not using Evolver or something like this for this, are you?
Using what?
Well, I know that people use Evolver for things like this. You can even use Evolver for, spine. It's a bit of, never mind.
Okay. Yeah. So I just, took a local minimizer LBFGS and wrote my code around it. So some of it was stolen from David Will's group. I was allowed to use their code. So it was implemented inside the so-called GMIN code from David Will's group. GMIN obviously standing for global minimization. So I incorporated my things into that, and so it's a combination of using local minimizer and doing a bit of your own coding there. So